Okay, today's lesson is going to be 4.5b, sketching polynomial functions. So what the idea here is that you're going to be able to make the sketch of a function to the best of your ability without getting too specific, but we will use our ability to factor in the zero product property to get us where we need to be. Okay, so first of all, it says find the zeros of that function, then sketch the best graph that you can. So if you're going to find a zero, we got to remember that that f of x will become a zero. Let's go ahead and rewrite this. And let's factor. Okay, what do you think the greatest common factor is going to be in this? Yeah, let's factor out a -2. It's going to make an easier problem if you take out the negative. Now, after you do so, you're going to be left to the trinomial. I made a little mistake there. Hold on. That's not 16, is it? It's going to be -8. All right, so there's your trinomial. What I'd like everybody to do is factor that down. As a normal trinomial. Okay, let's think about what two numbers are going to multiply to give you 16, add together to give you -8. All right, it's going to be -4 and -4, right? Okay, now what I'd like everybody to do is use your zero product property and get the rest solved. Take what you want. Okay, so at this point, set all of our factors equal to 0. But what you can see at this point is this is an extraneous solution. The other factor can be solved by moving 4 to the other side. But before we go any farther, notice that there are two of those factors. So once again, what we have is this idea of duplicity. These will be double zeros because they occur twice. So let's go ahead and take the square root. And what we will have is you will have 2 2's and 2 -2's. We could just list those as double zeros. Now, those are x-intercepts. What we can do is we can plot those as points. 2 and -2. Next step, let's try to sketch a graph. Now, what you can do and what might be asked on the ALEX program when we get to doing a review of this is that you could also find a y-intercept, which is simple. Y-intercept means you just plug in zeros for x's. The problem with this sketch right here is I won't be able to fit -32 on this graph. We will talk about that more in depth later when we work on ALEX. So how am I supposed to make a sketch of this thing with just 2 points sitting out there? Well, we got to go back, revisit end behavior. What is the degree of the original function? Here it is. The degree is 4, isn't it? And that is even. Now, what that implies to us is that if it's an even function, we try to break that down and relate it to the most common basic even function that we have graphed, which would be x squared, a parabola, a quadratic. So it will either look like something like that or like that with its end behavior. There's one more thing we can do to give us a hint as to what the sketch may look like. How about the leading coefficient? In this case, it's this -2. So that's a negative number, which implies that the graph would be upside down. So our graph should look like that. One more thing I want to focus on. The duplicity of these zeros. Since they are double zeros, that means that the x-intercepts will look like little parabolas, like that. So you can go ahead and put that on your graph because there are two of them. Associate that with x squared. The other thing we know by studying end behavior, since the leading coefficient's negative and it's an even degree, the end behavior is going downwards in both directions. Now all we have to do is kind of make the sketch. There's parts in here already, right? So here we go. So come up from your arrow, attach into this 0. You're going to bounce down. Now here's the question. Where do we turn? Because we're going to have to turn somewhere to come back up. That we do not know. So we're going to guess. And then we're going to come back down until we hit the other arrow. And we got a pretty good sketch. So let's talk about this for a second. This right here is called a local minimum. It's not the absolute lowest point, but it is locally the lowest point. We could get close if we made a table of values and chose values of x and try to narrow it in to where they stop decreasing and then start increasing. Or we could use calculus, which we have not learned yet. At this point, let's just make a guess. I've taken the time to graph that on Desmos. Let's see how close we are. Okay, here it is on Desmos. I could raise this up a little bit, maybe zoom out. All right, there you go. Well, we're not too far off, are we? Our turning point, our local minimum, we're off a little bit on that. But we did know that the y-intercept was -32. We just couldn't fit it on the graph. So it's a pretty good sketch, right? So that's the idea. Can you use your ability to understand end behavior in conjunction with factoring and the zero product property to make a decent sketch? I think we've accomplished that. Let's try a couple more. How about this one? Here's the original function. Let's factor it. So let's set it equal to 0. So let me move that down and get out of the way. What is our greatest common factor? If there is one. In this case, there is. It's a 3, isn't there? Let's factor that out. All right. Let's take it another step. And let's factor that trinomial as if it were quadratic. Okay, everybody. Let's get two numbers that multiply to give you 1, add together to give you -2. It's going to be -1 in both cases, isn't it? We're at a point now where we can solve this. Our factors are at most quadratic, I should say. So the first answer is going to be extraneous. Throw it out. The next one, we see it occur twice. So we will once again have some duplicity. Let's solve this. Okay, I'm going to write this as a solution set again. So there will be 2 1s. Those are double zeros. And 2 -1s. All right, now we can go ahead and graph those, 1 and -1. And then once again, if you thought about, what about a y-intercept? Let's look back at the original function. What if you were to substitute zeros in for the x's? Wouldn't you get 3 as an answer? So if you wanted to, we could fit that one on the graph. It's going to pass through the y-axis at 3. We know that for a fact. So we have our intercepts. To assist us in graphing this further, let's consider the end behavior. What is the degree of this function? It's 4. So the degree is even again. To us, that means it might look like that for the end behavior. It might look like that. What about the leading coefficient? Now, it's a +3, right? It's positive. So which one of those pictures will it look like? Eventually, it will end up looking like that. So we know to put some arrows up here to the left of that point, to the right of the rightest most point. it's got to end up traveling in the upwards directions. Both of these zeros are double zeros, so they've got to look like little parabolas when they hit the x-axis. Now the last thing to do is fill in all the spaces. And this one looks like it's going to be pretty easy. So this is going to travel down. It's going to hit that x-intercept. And now I bet it turns there. Now we don't know for sure, but we got a pretty good idea. And I think we've got a pretty decent sketch without making a table of values. All right, let's take a look at that on Desmos. Let's see how close we are. Let's turn that one off. Let's reset my coordinates. Here it is. And wow, we're right on the money actually, because we did know the y-intercept. This is what's known as an even function. I know the degree is even, but it's an even function also, which makes it symmetrical with respect to the y-axis. So we'll talk about that a little bit later. But we did a pretty good job. Let's go back to the presentation. And let's try one more. So using all of the skills that we have attained, let's see if we can do this. All right, let's start off by factoring. Is there a greatest common factor? I think there is. I think it's x. Let's factor out the x. Let's continue factoring this trinomial a little farther. All right, I need two numbers that multiply to give me -6. Add together to give me 1. I think that's going to be, hold on a second, please. Okay, and we're back. Sorry, an interruption to the recording. So we are checking out this, right? We have to get our factors in here. So let's do +3 and -2. And we are all set to solve this. So here we go. 0 equals x. X plus 3 equals 0. X minus 2 equals 0. All of these are single solutions. There's that one. Take away a 3 from both sides. That, add 2. Okay, we've got our 3 x-intercepts. Let's plot them. -3, 0, and 2. Let's go back to the original function. Can we find a y-intercept if we plug a 0 in for all the x's? And the answer is yes, it's going to be 0. We already have that point plotted. So next thing to do is consider end behavior. The degree of this function is 3, which is an odd number. So the degree is odd. Now let's think back to the most common odd function that we know of, which is a line, right? X to the first power. Lines are going to basically look like positive slope or negative slope. Let's look at the lead coefficient. It is a 1. You see that? The leading coefficient is a positive number, +1. That would correspond to a positive slope. So knowing that, I'm going to go to my graph, and I am going to have an arrow to the left of the leftmost point down here, and to the right of the rightmost point up there. Every x-intercept is going to look like a line. The only thing I don't know are turning points. But I know I'm going to start down here in the bottom left and end up in the top right. Let's go ahead and give it a go. So I'm going to pass through the x-axis. It's going to look like a line on every one of these. So here we go. Okay, where does it turn down? I don't know. I'm going to guess. Where does it turn back up? I don't know. I'm going to guess. So it's going to look something like that. We talked about this before in the other problem. This and this, those are called local extrema. In other words, this is the local maximum, This is the local minimum, not the absolute highest and lowest points. We could guess what those are with a table of values, or we could use calculus, which we don't know yet. But that's a pretty good looking graph. Now, what we need to do is compare that to something on Desmos to see how accurate we are. So take a good look at that. Let's go to Desmos. Let's reset our coordinates. Maybe zoom out a little bit. Look at that. We're pretty darn close, aren't we? A little bit off with the extrema, but overall, pretty darn good graph for what we can do. Okay, that's the presentation. Time for you to work on the assignment.